A pendulum has a frequency of 0.5 hertz. What is its period? A 2 hertz, B 2 seconds, C 0.5 hertz, D 0.5 seconds, or E, trick question, you can't have less than 1 hertz. Survey says 2 seconds, that's what I'm going for. T is equal to 1 over F. And so you can have a fractional frequency, 1 over 0.5, you get 2 seconds. So this is data that you might take next week or something, where you've got a hanging mass bouncing up and down on a swing. And so actually the vertical axis here is the vertical position, which we labeled x, but it could be y. And x equals 0 has been defined to be the center of vibrational motion. The mass was taken to about 6 centimeters above where it hangs at equilibrium, and then it was dropped. What's the frequency? Survey says 0.8. So I liked that. Basically, I think that this is sort of about, t is approximately 1.2 seconds, and f is equal to 1 over t, right? So 1 over 1.2. It's approximately 0.8. And then next question is same exact graph. What's the amplitude? Yeah, I was going for not 6 meters, so I think that it's a little hard to see that, but there's a tiny little 10 to the minus 2 up here. That was kind of key. This one's a matching question. You're picking which of these things are variable, which of these things are constant, and which of these things are functions. Okay, x is a variable because it changes with time. A is a constant because it's the amplitude, and it actually can change with time if it's not simple harmonic motion, like if it's damped motion, so that in real life, these oscillations will slow down after a while and stop. But in this equation, it's a constant. Cosine is a button on your calculator. We call that a function. What it does is it changes one number to another number. Your input and its output. Pi is a constant, obviously, and capital T is a constant. Oh yeah, that's the period. Once again, that doesn't change over time, same period. And then, I guess, lowercase t is certainly a variable. Which of the two constants, A and T, in the description of simple harmonic motion is determined by the initial position and velocity of the mass? Only the amplitude. So that's correct. The period is not determined by the initial velocity and position. Assuming that Hooke's law is still obeyed, then the thing to remember here is that the period and the frequency, actually, because the frequency is 1 over the period, they are set by the properties of the system. A ball of mass m oscillates on a spring with a spring constant of 2.0 times 10 to the 2 newtons per meter. Let's write that in regular language here. 200 newtons per meter. The ball's position in meters is x equals 0.35 cos 15 times t, where t is measured in seconds. So, recall, our equation for simple harmonic motion is that x is equal to a times cosine of 2 pi little t divided by a capital T, where t is the period, capital T is the period, lowercase t is that time, it goes ticking by, and so you'll see x go up and down. And a is the amplitude. What is the total mechanical energy? And here's that equation. 12, and drumroll, yeah. I think just by comparing these two equations, I think that this is A. A is equal to 0.35, and it must be meters. That's what's going on here, is x is a position. So this position is a cosine curve. Cosine just goes between +1 and -1. It's a dimensionless function, but then you multiply times the amplitude, and the x is oscillating between +a and -a. And then you get to basically choose. The total energy equals either 1/2 k a squared or 1/2 m v max squared. It's your choice, because they're both the same. They're equal. It's a constant of motion. And which one should we use? I think this is the one, right? Because we don't have v max. No one gave it to us. So let's use this. We'll say E is equal to 1/2 times k, which we have, times a, which we have, squared. So 1/2 times 200 times 0.35 squared. So you do need your calculator for today. And I got 12.25. And you know that the energy is always in joules. So hopefully meter what Newton per meter times meter squared. Actually, one of the meter squareds will cancel the meter on the bottom, and you'll get newtons times meters, which is joules from the work equation. Two pendula have same length, but different mass. The force of gravity, F equals mg, is larger for the larger mass, which has the longer period. Survey says neither. So what John set up here is actually almost a kilogram mass. It says 784 grams, a lot heavier than this one. And so if you displace them, certainly the force I can feel pushing back on this silver one is a lot bigger, but when you release them, they all slide together. It's just only the length that matters. A person swings on a swing. When the person sits still, the swing oscillates back and forth with a certain period. You can either sit in the swing or stand on the swing is what I meant there. When you stand on the swing, does that change the period of oscillations? People were saying smaller period if you're standing up. And I guess what I was thinking there, I can draw it on the other slide. So here are twos that are the same mass. I think if you stand on the swing, what's changing there is your center of mass is closer to the top of the swing where it's stuck. So it's like you're effectively reducing the length of the pendulum. Okay? So the period's a lot less for a shorter length pendulum. So that's all. T is equal to 2 pi times the square root of L over G. G is just 9.8. And L is the length. So if you've got someone who's properly sitting on the swing, not sitting still, but sitting, and there's the center of mass, then there's sort of like an effective length L from here to here. But if you have the same swing and they're standing up, the length is less. Effective length is reduced. So you get smaller. Let's say you've got a grandfather clock and you have always, I'm from Victoria, we're right down by sea level, and it's been calibrated so that it ticks at the right rate. And now I moved to Calgary, where it's 1 kilometer above sea level. Do you think that the clock will run fast or slow or normally? Yeah, I also voted for slow. T is equal to 2 pi times the square root of L over G. G is the issue here, right? So what I think is that farther from the center of the Earth, it's not 9.8, it's a little less than 9.8. Gravity is less in Calgary than it is in Victoria is the idea here, but just a bit. So, and you can measure this, G is less. There's actually a second-year lab experiment where you measure the acceleration due to gravity very, very precisely, and then you go up the stairs of the Burton Tower and watch as G decreases as you get up to the 13th floor. So, what does that mean? If G is less, then T, it's on the denominator, so T is more. So what does that mean? Well, I would think that the normal thing, the period is the time between ticks, right? So you'd go tick, tick, tick. And then what will happen is that in Calgary, it'll go tick, and then a little longer. Tick, and a little longer. Tick, and you're late for work at some point. What is a transverse wave? Survey says that a transverse wave is a wave in which the medium oscillates in a direction that is perpendicular to the direction that the wave travels. What I've given you is the history graph of the left end of a 12-meter long rope. It's going to start at 0, and then I'm going to slowly go up and then snap it down, back down to 0. It's going to take 2 seconds to go up. And then at t equals 2, it goes quickly down to t equals 3, it ends up there. That's the left end. And then the wave velocity on the rope is plus 2 meters per second. It's moving towards the right at plus 2 meters per second. So which of these graphs in the bottom gives you the snapshot at t equals 5 seconds? Survey says sort of scattered all around. A lot of people are choosing D. This leading edge is shallow. It's not as steep, I guess. Is at x equals 0 at t equals 0, since this whole thing is the snapshot of the x equals 0, it's a histograph at the left end at x equals 0. So at t equals 5 seconds, it should have moved. The distance, d, is equal to v times t. So it's 2 plus 2 times 5. It should be way over at 10 meters. So we want something where the shallow end of it is sitting at 10 meters. Well, it's either this one or it could be this one, I guess. That's where the wave is just about to hit. And then the other thing is that I don't think this one's flipped. Not flipped. So what I want is the shallow end, right? So it can't be this one, it can't be this one. And so I think it ends up being this one. So this one hasn't gotten far enough, but it's the right shape. But since it's going 2 meters per second, it should be there. And then at 3 seconds, I've finished this pulse, and it's down at the bottom here, the x equals 0. And so, and then there's another 2 seconds to 5 seconds. That should have moved 2 times 2, should be 4 meters away. So it does make sense, again, that the end of the wave is 4 meters away from the end. Again, conceptually, if I have a wave which is traveling to the right, so that means the crests go to the right, and the troughs, the whole pattern goes from left to right. There's a piece of the string marked with a dot. In what direction is that piece of string moving at this instant? Sorry, guys. Every particle is moving with simple harmonic motion. So if it's at its equilibrium position, it's definitely going at its maximum speed, either up or down. So the question is it up or down? So follow me so far? When you're at the top of your simple harmonic, your high maximum amplitude, you have 0 velocity momentarily because you're turning around. Bottom, negative A, you're going to have 0 velocity again because you're turning around. If you're at the center, you're either flying through equilibrium on the way up or flying through on the way down. Now, it's not easy to figure out which one of these it is. The way I figure it out is I say, okay, notice every single particle on this wave is just going up and down. Nothing is moving from left to right. Nothing. Except the pattern, I suppose. I mean, it kind of looks like something's moving that way, but nothing's moving that way. It's the energy. Okay? I sometimes think I can give myself a high five if I go, oh, high five. Oh, I felt it. So that energy somehow got to my hand. It's like action at a distance, right? But only things moved up and down. It's kind of weird. But anyway, so this is like now. And then later, we choose a different pen color, like this green, we can do later. So where does that particle have to go to be on the later? It has to go up to stay on the pattern. This particle has one job. His job is stay on the pattern. So he has to be going up. There are all these, it's like the pattern is moving along and all the particles, like you imagine being the wave, right? You have to go whoa when the thing comes by. So, to stay on the pattern. All right, so let's keep going here. You've got a traveling wave. It's got a certain speed, wavelength, and period, and it was created by an object which is oscillating with simple harmonic motion, maybe the speaker or something. Something's oscillating, and it's creating a wave that's going along. If you then decrease the period of the oscillator, what should happen to the speed of the wave? Speed should increase, decrease, or remain the same? I'll tell you guys the answer to this one. It's C. The speed should remain the same. So it is true that V is equal to lambda divided by T. But that doesn't mean that if you change the period, that you change the speed. What happens is you also change the wavelength. So the wave speed is determined by the properties of the wave. The wave speed is set by the properties of the medium. So the question is, if the period decreases, what should happen to the wavelength? People are saying wavelength should decrease. So that's exactly right. Basically, the constant here is going to be the wave speed. It could be the speed of sound. It could be the speed on a string, which is determined by the tension, actually, that's in the string. 2 triangular wave pulses, which are heading towards each other. And you know they both travel at 1 meter per second. And these are all snapshot graphs. So you're in each of these diagrams, you're plotting y on the horizontal axis and x, the actual distance. Sorry, y in the vertical axis and x, the actual distance on the horizontal axis. So it's just like you've looked at it at a particular instant. And the instant for the top is t equals 0. And they're asking which of these choices, A, B, C, or D, would be what the string would look like at time t equals 6 seconds. Ooh, it's sort of a big mix. I thought C, so I tried to count 6 meters to the left for this pulse that's going to the left, and then 6 meters to the right for the pulse that's going to the right. And the way I got it is that there was sort of this pulse and this pulse. Their width is still going to be looks like 5 meters. But when you add it all up, you just kind of trace it along to about here. And right about here is where this one starts going down and this one starts going up. And I think they kind of cancel each other out. So that here, this halfway to this halfway gets to about there. And ends up with a kind of, I think, a flat. So at every point, you're just adding the two waves. Want to do another one? This one is showing two opposite-signed triangular pulses on a string approaching each other at, again, 6 centimeters per second. Shown is a snapshot graph at t equals 0. And the question is, at what time will the displacement on the string be 0 everywhere? A lot of people are saying 1.6 seconds. So I agree with that. I think that the distance actually is looks like 19 centimeters between them at this point. So d equals 19 centimeters from here to here. And the relative speed is going to be 6 minus 6 is 12 centimeters per second. The v relative is going to be the distance between them right now divided by the time. So the time is going to be d divided by v relative. So 19 centimeters divided by 12 centimeters per second. And I got, makes sense. At that point, the upward triangle is going to overlap with the downward triangle, and they're going to perfectly cancel each other out. Just for a moment, and then that energy will come back as the pulses pass right through each other. Let's say you have a standing wave, and it's in its third harmonic. And the frequency of the third harmonic, F3 or something, is 27 hertz. So what would the frequency be of the seventh harmonic? 63, wow, so that's good. Yeah, the first step was to find what the fundamental frequency is. So if you know the third harmonic is at 27 hertz, that's 3 times whatever the original, like the fundamental frequency was. So 27 divided by 3 is 9 hertz. So 9 hertz must be that fundamental frequency, F1. And then once you've got F1, any harmonic, seventh harmonic is just going to be 7 times that fundamental frequency. 7 times 9 being 63. It says the middle C hammer of a piano has 2 strings, and it produces, these 2 strings produce a beats of 1.5 hertz. That's the beat frequency. And you know that one of the 2 strings is at 260 hertz. What frequencies could the other string have? Yeah, that's what I was looking for. The idea is that F beat is equal to the absolute value of F1 minus F2. And so we don't know whether F2 is higher or lower than F1. But what you can really do if you're tuning a piano, you can then take the string you don't know and tighten it, which you know will increase the frequency a little bit. And then, depending on whether the beat frequency goes up or down, you know if you're getting closer or farther away from the known frequency. So you can resolve it by just changing one of these a little bit, and then you'll know if you're above or if you're below. So see if you can picture this one. You got a speaker that's sort of just in the middle of space, like it's hanging on a wire. It's in the middle of a giant auditorium, and it's at a distance of 9 meters away from your ear. So I would say that you can imagine a giant spherical bubble. There isn't really a bubble, but if there was one that was centered on the speaker with a radius of 9 meters, it would have a surface area of 1,000 square meters. When turned up to maximum volume, the speaker outputs 40 watts of sound power, I guess, or energy in the sound waves. So what's the intensity? Yeah, you just do the 20 watts divided by 1,000 square meters. That's how much the power has been spread out. So you end up with 20 milliwatts per meter squared. And that'll give you some indication of the loudness.
My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.